Welcome. Today's lesson is entitled Compound Interest. There's really some fascinating mathematics that relates to the concept of compound interest. So just grab a graphing calculator and let's see what develops over the course of this notes worksheet. So at the top of your page, it starts out by saying compound interest is a particular type of exponential growth. So what that means for us, of course, is that it is going to be a percent increase over the course of a time period. So percent increase, in this case our time period will be in years. So a percent increase per year, so that's going to be our exponential growth. But here's where it diverges a little bit, so just kind of underline that piece if you would. That percent increase is going to be broken down into smaller increments. And I'll show you what that means as we go through a few investigations today. All right, so get that piece in if you would. And it looks like we have this investigation at the top here. So let's go ahead and take a look at what this is and just really an introduction to what compound interest would entail, and then we'll dive a little deeper with the next investigation. So it says, imagine you deposit $1,000 into each of two accounts. The first account pays 12% annual interest once per year. The second account is going to pay 1% every month. Determine the balance of each account after 1 year. All right, great. So it looks like just straight up exponential growth, but we're going to only track it over the course of one single year. And so we're going to start out with an initial quantity. Let's do the easy one first here, which would be the first account. And so it looks like just the hypothetical $1,000 goes in. And so that's going to be our initial value. And it's going to increase by 12%. So what that, of course, translates to for us, as we've been working on this over the last few lessons, is a growth factor of 1.12. Now, if I'm just going to apply this growth factor at the end of 1 year, and I want to find the balance at the end of that year, it looks like I just want to raise it to the first power. So 12% annual interest once per year, and we're going to just see what the balance is after a year. So we're going to only apply this growth factor once. All right, well, I'm going to bring up my calculator here. And let's go ahead and see what we have going. So I've got my $1,000 right here times 1.12 raised to the first. And when I do that, it looks like we get a balance of $1,120. So let's go ahead and write that in right here if we would. And that looks great. First account, not too bad. Increased by 12% over the course of the year. What that would mean is the ending balance would be $1,120. Now here's what's kind of interesting about the second account. The second account, also pays 12% at the end of the year. It just so happens that that 12% is divided up every single month, and you get 1% each month. And so the question, of course, is, if that also pays 12% per year, do I end up with the same amount? Well, let's see. So, of course, we start with $1,000. And in this case, as you can see, the growth factor is going to be 1 plus the 1%, so 1.01. And I get that 1% every single month over the course of a year. And so how many times do I apply that growth factor? And it looks like 12. And so it looks like the calculation is slightly different. The question, of course, is, do I get the same result right here, or do I get something different? So let's go ahead and take a look at that piece. I'm going to go ahead and type that in as well. So here's my 1,000 times 1.01, raise it to the 12th, and notice what we get. Something a little different. In fact, a little greater than what this one was. So we get $1,126. I'll round to 83 cents there. That should be fine. All right, so let's put that in. And you know, obviously, the question is coming. So let me go ahead and read it. As I specified, both accounts pay 12% annual interest. And the question, of course, is, why was the interest greater in the second account? Why did we make more money in the second account as opposed to the first account? So think about it for a minute. And, you know, when I write my stuff in here, if you want to go ahead and paraphrase it, that's perfectly fine. But really, we want to get down to the idea of what compound interest means. All right, so what do you think? Why did we make more in this account compared to this account right up here? And I guess what I would say is, to get into the specifics, we got an interest payment at the end of the month, right? So we got an interest payment, say, at the end of January. So the interest paid, and let me actually write that in there. Hold on one sec. The interest paid in January got to earn interest the rest of the year. The interest paid at the end of February got to earn interest the rest of the year. The interest paid at the end of March got to earn interest at the end of the year. Interest earned interest. So let me write that in. Interest paid in January and February and March, etc., all the way through, earns interest the rest of the year. Sorry, let me get that in for you properly. There we go. Whereas the first account, we only got one interest payment over the course of the year. So as a result, only the principal, this $1,000 right here, was able to earn interest. Whereas here, when we got that first interest payment, that earned interest the rest of the year. The next interest payment, the rest of the way, that interest got to earn interest. Interest earning interest. And so, long story short here, this effect is known as compounding. Interest earning interest. Sorry for being redundant, but you'll probably hear me use that phrase over the course of this lesson. Wonderful. So basically, we're going to talk about two different rates today, and what's called the nominal rate. And as a matter of fact, in each case, the nominal rate here was 12%. And what that basically means, it's the interest rate before the compounding takes effect. So I'm just going to write before compounding right here. And again, annual interest was 12% right here. Annual interest was 12% for this one. Okay, so the nominal rate in each case was 12%. But because in the second account the interest got to earn interest, the effective rate, really the true growth rate, is really after the compounding takes effect. So write that piece in if you would. Now it just turns out for the first account, because the interest never got a chance to earn interest the rest of the year, the effective rate turned out to be the same as the nominal rate, 12%. But in the second account, because the interest did get to earn interest the rest of the year, we were able to earn a little more than 12% over the course of the year. The true percentage increase was more than 12. Now, I'm going to go ahead and just put the percent increase right here, and I'll tell you where I got this number. But it would be this right here, about 12.683%, give or take. And as a matter of fact, to just get this number from my calculations up here, it really just goes back to an old middle school calculation. It's just really the percent increase. And you don't have to write this down if you don't want to, but if you do, it's not a bad idea. So basically, all I did to find out the true percentage increase was take the difference, the new minus the old, divide it by the original, and then I just converted it to a percent, so I just times it by 100. So that's how I just got this piece right in here. All right, perfect. So as you can see, interest earning interest, what that does is it changes the growth rate. It's more than the annual interest specified in the problem. Okay, very nice. Now the next investigation is kind of the big one. So now what we want to do is really take a look at how the effective rate changes based on the way we compound. So as you can see, the title is The Nature of Compounding, and we're going to take a look at that effective rate in just a little bit. So let me just read what we have here, and then we'll just fill in the table to the best of our ability. It says, let the nominal rate, so of course, as we said, the interest rate before compounding takes effect. We'll just make it be 6%, nice easy number. Fill in each column, and you'll see on the last one why I say this, the last column to 9 decimal places when appropriate. All right, first and foremost, put a little asterisk, if you would, by that effective rate. That's the one I really want to focus in on. And then in this case, we're going to go column by column. And I'll tell you what I want you to put in each case, starting out with the nominal interest rate right here, which according to the problem is going to be our 6%. And if you get a chance, everybody, can you put a little R for me above that? When we develop our formula for compound interest, you'll see this nominal interest rate is going to be denoted by our variable R. Okay, so anyway, let's go 6% on each. This one's easy. So just 0.06 all the way through, if you would please, that would be great. All right, no problem there. One down, and it was easy. So 6% increase, perfect. Now this is going to be the good one right here, because this is going to affect this over here. So what this means, the number of times compounded, is really the number of interest payments we get over the course of the year. And as you'll see in our formula on the back side, we're going to denote this with n. So put a little n above, if you would. So again, one more time, it's the number of interest payments we get per year. So if it's compounded annually, that just means we only get one interest payment over the course of the year. And as a matter of fact, if you go back to that first investigation, that was the first account. We got just one interest payment at the end of the year. That would be compounded annually. Quarterly, that would be 4 interest payments over the course of the year. Monthly would be 12 interest payments over the course of the year. And by the way, this was, of course, the second account in that first investigation. We got that 12% divided up 12 times over the course of the year. So there we go. That was the monthly piece. Weekly, we really don't see weekly, but I'm going to go ahead and throw a 52 in right there. Now daily, it's going to seem a little weird for this investigation, but I'm going to throw in 365 and include the leap day, so 365 and a quarter. And what I want to have happen, of course, is I want n to get larger and larger and larger. So what happens if I get an interest payment every single hour? Well, what that would mean is that I would get 8,766 interest payments over the course of the year. What happens if I get an interest payment every single minute? Well, if I got an interest payment every minute, this is how many I would get over the course of the year. Over 500,000 interest payments. Now, I kind of stopped at every minute, but theoretically, could I keep going here? Could I do every second, every millisecond, every nanosecond? And if I do that over here, do you see obviously that n would be getting larger and larger and larger? And that's what I want to explore. What happens when n gets larger and larger and larger? So here I went from 1 to over 500,000. Theoretically, we could keep going and going on this. Okay, let's go get this next column. So remember how I started out the lesson, everybody. It's a percent increase per year, but it's broken up into smaller increments. So for annually, well, this one obviously is pretty self-explanatory. That 6%, I get all at once. I get all at the end of the year, just like I did in that first investigation with that first account. But quarterly, it's not like I get 6% each quarter. That would be nice. But that 6% is divided up over the 4 quarters. So I get 1.5% at the end of March, 1.5% at the end of June, 1.5% at the end of September, and 1.5% at the end of December. So that 6% is divided up 4 times over the course of the year. Okay, if it's monthly, again, I don't get 6% every month. I get a 12th of the 6% every month. So I get 0.5% at the end of January, 0.5% at the end of February, et cetera, all the way to 6%. So do you start to see that idea of compound interest? It's a percent increase, but it's broken down into smaller increments. That's the case that we're seeing here. Hope that is now really starting to click. So let's go ahead and fill in the rest here. Hopefully not too bad. And last right there. Looks good. Okay, so you could see obviously as we get this, as n gets larger and larger and larger, the percent per unit time is going to get smaller and smaller and smaller. All right, now the growth factor, of course, just builds exactly on this one right here. We all know a growth factor is really 1 plus the percentage. And so in this case, guys, nice and easy, let's just do 1 plus that percent per unit time. So that's how I'm going to get my growth factor. Just add in the 1 on top of it. Obviously, division comes first, so we kind of have to write it like this. And let's see what we have going. Again, I'll try to be as quick as possible. You do the same. Let's see if we can all get this in here in a relatively painless fashion. All right, 2 more for me. And then the last one is the key one right there. So get your hand all loosened up. All right, so now, guys, the effective rate. And so what the effective rate means is really the true growth rate over the course of the year. So this and this really starts to affect this piece right here. And so let's go ahead and start this out. I'm going to do one at a time, and then we'll just kind of cut loose and fill in the rest of the table. But essentially, that's my growth factor. And the question I would have for you in terms of each of these is how many times do I apply the growth factor over the course of the year? Well, obviously, everybody, if it's annually, then I only apply it once over the course of the year. So I'm going to raise it to the first. Now, I don't even need a calculator for this. If I did this on the calculator, I would just get 1.06, which, of course, if you kind of exclude that 1 right there, is 6%. So if it's compounded annually, the effective rate is, of course, the same as the nominal rate because the interest didn't earn interest over the course of the year. All right, but now watch what happens. So let's go get this one, everyone. 6% divided 4 times over the course of the year. How many times do I apply this growth factor by the end of the year? 4 times. Does that make sense? Okay, well, let's grab the calculator and do it. So I'm going to do parentheses, nice and easy, exactly what I have on my board. So there is my growth factor, and I apply that growth factor 4 times over the course of the year if it's compounded quarterly, and notice what I get. If you sort of get rid of the 1 for just a second in your mind, look at this as a percent. Is it exactly 6%? No. Because the interest gets to earn interest over the course of the year, it's more than 6%. So, sorry guys, I'm going to ask you to write that entire number down. You'll see why as we go through the process here, but I get 1.0613635551, something along those lines right there. Okay, good. Now, I guess I would ask you this even before we do the calculation. Do you think if it's compounded monthly, do you think our effective rate's going to be greater than or less than this value right up here? Should be greater than, right? The more chances that the interest gets to earn interest over the course of the year, the greater the effective rate. But let's see by how much. So one more time, I'm going to bring the calculator up, and then we're just going to go ahead and write in the remaining ones. So divide that by 12, and then, of course, raise it to the 12th, and I end up getting this right here. All right, so I've got this one compared to this one. Look at this. It's definitely bigger than the previous entry, but you have to go back a few decimal points to see it, right? So there it's the same, there it's the same. I have to go 4 decimal places back just to see the change. But it is greater. It is greater. So let's get that in there. And it is 1.061677812. All right. So you can see. Obviously, let's just come up with a quick conclusion, and then we'll just jot in the rest here. The more times that it's compounded should be a greater effective rate because the more chances the interest gets to earn interest over the course of the year. All right. Well, let's go put in the remaining ones. This is what I have on my paper, so you can go ahead and do this with me if you'd like. If you want to do some calculations yourself, that's fine. I get 1.06179982, something like that. Hopefully these are right on target. I'm just going to go through the remaining ones as well here. Hopefully we can fit this in. And you should see just a little bigger each time. So 1.06, 1831, 314 for that one. Getting closer, 2 more for me here. Raise it now to the 8,766. If I did that, I get 1.061836,329. All right, so you notice n is getting larger and larger and larger. Look at the effect that it's having on the effective rate. Yes, it's increasing, but not by much. And watch this last entry. We're going from about 9,000 interest payments over the course of the year to over 500,000 interest payments over the course of the year. And does it have that much of an effect? Well, let's find out. So when you do this one right here, kind of the last entry in the table, and as I mentioned, theoretically we could keep going every second, every millisecond, every nanosecond, and watch n get larger and larger and larger. But if I do this one right here, I get 1.061836,534. So one more time, guys, think about this. We went from about 9,000 interest payments per year to over 500,000 interest payments per year. Did it have a dramatic effect on our growth rate? Let's see how far back we have to go just to see the change. 1, 2, 3, 4, 5, 6. I have to go 7 decimal places back just to see any change whatsoever. That's how close that is. So even though this increased dramatically, this does not. Wow, pretty cool. Okay. Well, everyone, it's time to start putting our formula together. So let's go. So on the back here, letter A. Based on the information in the table, find a formula for the balance of an account paying R% annual interest. There's our nominal rate, everybody. N compounding periods. And now we're going to explore it for any number of years. So there's our independent variable, our T years. What I want to do first, though, is put in the effective rate, kind of the true growth rate right there. And so if you kind of look at this, using R and N, think about what this effective rate is right here. So what is that effective rate? Think about R and N in each case. And I hope you noticed in each case, that's our R on top of the fraction, and that's our N on the bottom of the fraction and the exponent. So take a look, and if you need to look at this in a little more detail, please do so. But the effective rate essentially is this right here. That is how we measure the true growth rate over the course of a year based on how it's compounded. 1 plus R over N to the N. All right, very nice. Now what we want to do is expand this out a little bit and get the balance of our account. Now start putting money into the account and tracking it over the course of any number of years. So here's what I'm going to ask you to do. And just very lightly, because I think we're going to erase it momentarily, but let's just write y equals a times b to the x. Because remember, compound interest is just a very particular type of exponential growth. So the formula is the dependent variable, which is the balance. Typically you see it as a, maybe kind of the amount. Little a right here, of course, is the initial value. In the compound interest formula, it's P for principal. So you're going to see P here, the principal. Now the B, of course, is the growth rate, right? Now everybody, here's this piece. That is the growth rate. That's what we took so much time exploring. So that's the growth rate right there. So it's P times 1 plus R over N raised to the N. That's our growth rate right there. That's this piece. And then last, everybody, is the independent variable, the time. And again, now we go ahead and do it for any number of years. And so I have a little t right there as well. Y equals A times B to the x. And there it is. Looks great, doesn't it? Okay, well, I'm going to erase this. But just remember, compound interest is just a very particular type of exponential growth. It's when we have something that is broken down into smaller increments. Okay. I think we sort of already alluded to this one, but let's go ahead and read it and see what it says. Does the effective rate increase without bound, or does the increase level off? And as you can see, it seems to level off. We have to go further and further back just to see any change, even as the way we compound it gets larger and larger and larger. So, as it says, there is a limit to the effective rate for any given nominal rate, and the nature of that compounding is referred to as being compounded, and this is the phrasing you'll see, continuously. And so the idea behind this is that n gets larger and larger and larger. So the number of compounding periods, that's n, approaches infinity. And that's what I said in my table. I wanted to see what happened when n got larger and larger and larger. I only went up to 500,000. But again, theoretically, we could see what happens as it gets larger and larger and larger. But if you kind of think about it here, if you look at this great effective rate, and obviously my formula over here, I can put in larger and larger numbers in, but can I actually put in infinity? Does that make any sense whatsoever? No. And so what we want to do is have a way to approximate what would happen as n does approach infinity. And the way we do that, of course, is by using our base e. So watch what happens here. So we move on to this piece. And just one more time, there is a limit to the effective rate for any given nominal rate. And the nature of that compounding is referred to as being compounded continuously, really getting an infinite number of interest payments over the course of the year. And that's how we approximate the limit of our effective rate. And in this case, we're going to use our base e. So watch this, if you would. Let's take e, go get e raised to, and remember the nominal rate was 0.06 or 6%. Watch this. And look at that number for just a second. We're going to write it in there, and then flip it over and tell me, does it look just a little larger than the last entry in our table? Let's see. Well, first of all, let's put it in. So this right here, 1.061836547. That's what I have right here. So I'm going to go back just a second, if we could, and don't write this on your paper, but this was that number right there, 1.061836547. So take a look. Look how far back we have to go just to see any change from the last entry in our table. We have to go all the way back here just to see any change. Isn't that pretty amazing? Now I would ask you this. If we did 1 million times compounded over the course of the year, would it be bigger than this? Would the effective rate be bigger? No. What if I did 1 billion for n? Would it be bigger than this? No. 1 trillion for n. Would it be bigger than this? No. Everybody, this is the limit of the effective rate for 6% annual interest. I hope that makes sense. This is approximating what would happen if we got an infinite number of interest payments over the course of the year. Is that all right? There's your limit right there. Okay. Really, quite amazing. So let's see. Does this effective rate seem to fit the pattern in your table as its limit? You bet. Absolutely. So there is a slightly different formula for compounding a quantity continuously. So again, this would be approximating an infinite number of interest payments over the course of the year. That effective rate, which again is the limit of the effective rate for any given nominal rate, is just our e to the r. And then when we start to apply it with putting money in and tracking it over a course of a number of years, it becomes what people commonly refer to as the PERT formula. Okay, so two formulas. This one we would use for anything not compounded continuously. This is compounded continuously. All right, looks great. We're going to dive into the next piece here and do just a couple examples to wrap this up. So nice and straightforward, just really calculator oriented here from here on out. Let's see if we can put some stuff together. So $5,000 is invested into each of 3 accounts. Find the balance after 18 years. So now not just worried about the effective rate, but really tracking money and how it's compounded and based on the interest rate. Okay, so let's go get them. So if you would, just nicely write in here if you have a little room. Again, we're going to use this formula anytime it uses the word compounded. So if it's just growing by a certain percent, obviously we're just going to think of y equals a times b to the x. As soon as we see the word compounded, we're going to use this right here. So let's go ahead and get it. So we start with $5,000. That's your principal. 1 plus and 7.5%, so that's our nominal interest rate, so that's R, 0.075. If it's compounded annually, then we divide it by 1. And then just be a little careful. Your calculator is a little picky with this. So it's going to be to the NT, and actually I want to stay consistent here, so N come first. So 1 time per year for 18 years. Okay. Now, as a matter of fact, compounded annually, you can get away with just y equals a times b to the x, just because this is 1. But the fact of the matter is, as soon as I see compounded, I sort of revert back to this formula right here. Okay. It's just kind of setting up a formula. Let's let the calculator do the work on this. And I type it in exactly as I wrote it, everybody, and I'd encourage you to do the same. So 5,000, 1 plus 0.075 divided by 1, raised, and again on the 83s especially, you do need the parentheses there, 1 times 18. And when I do that, that's how much money I'd have in the account after 18 years. So let's get that in, just dollars and cents. If you could write it down as well, that would be great. So it is $18,379.02. All right. Now what would happen if it's compounded monthly? Do you think we're going to earn more or less than this number right here? Well, first of all, let's find out. So we already have the formula in play. So it is A equals, everybody let's get those same numbers going, 5,000, 1 plus 0.075, but now divided by 12 because it's monthly. And the idea is, how many times do I apply this growth factor? Well, 12 times per year for 18 years. So 12 times 18. All right, everyone, same thing. And again, what do you think? Do you think we're going to earn more money than our answer from Part A, or less, or the same? I don't know. Let's find out. So we've got that right there, 1 plus 0.075, divide by 12, raise it. Again, I do parentheses on that, and we apply that growth factor 12 times per year for 18 years. So 12 times 18, and there we go. Look at that. So quite a bit more money just over the lifetime of this account. So it ended up equaling $19,206.27. By the way, why did we earn more money in this account than this account right in here? Because, of course, here the interest was able to earn interest at a greater rate than it was right here. The more it's compounded, the more the interest gets to earn interest. Okay, but there is a limit, and that's the idea. There's a limit to it. And so now, to get that limit, we use the idea of being compounded continuously. So as soon as we see that phrasing right there, guys, we revert to the PERT formula. That would be this piece right here. And let's go ahead and get that in play. So 5,000 times E raised, and in this case, 0.075 times 18. So RT at the end there. And do you think it's going to be more or less than the 19,206? Should be more. And there it is. The more that the interest gets to earn interest, the greater the amount. So let's see what we have. In this case, 19,287.13. All right. So annually, monthly, continuously. Is there any way to keep everything the same? 5,000, 18 years, 7.5%. Is there any way to get more than this based on the way it's compounded? No. This is the limit, and I hope I've been pretty clear about that piece. So we could have gotten, I don't know, every minute gotten an interest payment, every second gotten an interest payment. And if we put that into our formula, we still would not get over this right here. This is the limit. Beautiful. All right, let's go get the next example. So example 2, $10,000 is invested in what's called a CD, a certificate of deposit, paying 3.5% compounded daily. I believe banks typically use 360 for daily, so I'll stick to the 360 there. Determine the effective rate of the account, and then use a graphing calculator to determine how long it would take for the balance to reach 15,000. Okay, great. So the effective rate, of course, let's go ahead and get this piece going right here. So we're not really tracking it over the course of any number of years at this stage. We're just looking at the effective rate, the true growth rate over the course of the period. The nominal rate, everybody, is 3.5%. But that 3.5% is divided 360 times over the course of the year, as we do get 360 interest payments over the course of that year. So that is my effective rate. That's what we developed on that front side with that long, great table. And that's what I'm going to calculate. So let's see what we end up getting. Again, 3.5% divvied up 360 times over the course of the year. Single year, that's what we're talking about, just the growth rate of the account, irregardless of the principal and the number of years that the money is in the account. All right, so let's get that. And as you can see, because the interest was able to earn interest, here's our true growth rate. Is it more than 3.5%? Here's your 0.035, but obviously there's more. So just depending on how we want to round it here, I'm going to do it like this. I'm going to write it two different ways. So 1.03562, I rounded right there, or 3.562%. Something like that right there would do. Okay, very nice. Now the next piece, of course, is to solve something like this right here. Let's see what we have going on. Now we're going to talk about the $10,000. 1.035 over 360 raised to the 360 times however many number of years. And we want to see how long, how many years it would take to get to 15,000. So I believe that's what we're looking at here, where I give you the output and you're trying to find the input, of course. So a little different than example 1. Now, we will find a way to solve this algebraically. Right now it's just a little bit beyond our scope. So we're going to use the graphing calculator as we have done once or twice before. So everyone, if you would, on your paper, let's go ahead and just write Y1, and we're going to type this in. So this would be going in the Y1, and in the Y2 would be the 15,000. Again, it's probably quicker and more efficient when we do this algebraically, but for right now, I don't think we have much choice in the matter. So we're going to go ahead and graph the right side, graph the left side, and see where they intersect. All right, well, I'm going to go ahead and do that here. And so go to the Y1 if you would, and let's type that in, 10 grand. And 1 plus 0.035 divided by 360, raise it to the 360 times the number of years. Excellent. And I want to see how long that's going to take to get up to the 15 grand. So, the only real trick at this stage is to go ahead and find a window for this. Now we're talking compound interest. So X is the number of years, Y is the balance. And so, just in this case, we're not talking about a tremendous number of years here. So I'm going to go 0 to 20 or 0 to 30, doesn't matter there. And I always start my account at 0, doesn't matter though. And I always leave a little room above where I want, just so it's not at the very top. So if I want to get to 15,000, I don't know, 20 is fine. But you can modify that if you'd like. Hit graph, and there we have it. Here's our exponential growth curve, by the way, to represent the compound interest. And here's our 15,000. Okay, again, we've kind of done this before, so second trace, let's go get an intersect on this. Enter, 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 and there we have it. About 11.59 years. So I'm going to go ahead and put that in right here. 11.59 years. All right, so if I give you an output, yeah, hopefully you're able to go ahead and see if you can find the number of years, the input that goes with it. And we'll come back to a problem like this and solve it algebraically. For right now, please use the graphing calculator. All right, last piece. Let's wrap this on up here. So it says revisit the number E. As you can see, E can be an integral part of compound interest, representing sort of the limit of an effective rate. And so now think of it this way. We've sort of explored this in a little detail. It's kind of interesting. We know that E is the limit as n approaches infinity of 1 plus 1 over n raised to the n. And so if I was to give a verbal description, and again, I'll just sort of be quick with this, and you can jot this in. And if you have a question on it, that's fine. Or if you want to look at it in more detail, that's fine. But basically, doesn't this kind of look like the effective rate? Doesn't that have that feel of that effective rate that we did, where n is getting larger and larger and larger? And n is approaching infinity, so we're going to talk about it as the limit. And take a look at this piece. What would be the rate? What would be our nominal interest rate with a 1 right here? Well, this would be 100%, right? And sort of one out in front, we never really talked about a principal with an effective rate, but essentially it's talking about it with the principal being $1. Okay, well, long story short, here's what I have. It is the limit of the effective rate. Again, it really has that same exact feel as that table we looked at on the front side. So it's the limit of the effective rate for $1, so kind of the $1 out in front, growing at 100% annual interest. R is 100%, P is 1, and there we go. N is getting larger and larger and larger. N is approaching infinity. Cool. Alrighty, well, I'll give you some time to take a look at that, try some examples, and please let me know if you have any questions over the course of your practice problems here.